Hello and welcome to the second module on association rule mining. In this module, we'll look at a very popular algorithm that's used for association rule mining. So as I said earlier, uh, the main problem in mining association rules is counting part. Right? So typically how we would do it is that you would generate candidate frequent item sets, right? And then count how many times they occur, right? And then you prune the candidates based on the count. So if the count is above a certain frequency, then you're going to call them as frequent item sets. And if they're below a certain frequency, you're going to reject them. But then the problem with doing such an approach is that you have a combinatorial number of candidates. Right? So think about it. Right? So you have like 10 different items from which your transactions can be drawn, and let us say you are considering 2 item sets. So that essentially gives you 10 choose 2 candidate item sets. Right? Now this is a small number. Think about real applications where these candidate sets can be in the millions. Right? So somebody like an Amazon or a Flipkart is going to have like millions of candidates. And how would you even generate candidate item sets which are more than this very small size of candidates? So you really need a clever way of generating fewer candidates. So the very first approach for looking at generating fewer candidates came about in the late 90s, which is the a priori property. Right? So the a priori property is a very clever observation. It just says that all non-empty subsets of a frequent item set must also be frequent. Right? Even if one of the subsets is not frequent, then I don't have to consider the larger item set. I don't even have to count the larger item set. Right? So the first paper that proposed this a priori property and came up with a fast algorithm for mining association rules was proposed in 1994, and it has been a very seminal algorithm. Right? They found first they introduced this problem of finding frequent item sets in a database of transaction. It set the tone for the entire field. In fact, this use of the term mining association rules almost was the reason for the whole subfield of data mining, right? And since then there have been numerous improvements that have been proposed on top of the a priori algorithm that allow you to mine really large data sets, scale up to millions, and so on and so forth. But still, the a priori algorithm is where we have to start our exploration into association rules. So in this module, I will talk about the a priori algorithm and give you a more like a introduction by an example, and so I'll leave it to you to look up other algorithms if you are interested in association rules. So here is we'll start off with a very simple example, right? So look at a very small transactional database. So it has got only 4 transactions in it, so each of a different ID, and there are a total of 5 different items which could be figuring in these transactions. So we're going to call them A through E. Right? So let's look at the set of 1 item sets. Right? So we have A through E, and just count the frequency of these item sets. Right? Let's suppose that I have a minimum threshold for the support of 2. Right? So I have 4 transactions. An item set can be called frequent if it appears in at least 2 of these 4 transactions. So you can immediately see that item set D is not frequent. So not only is the one item set D not frequent, any larger item set that contains D as an element in it can also not be frequent. Right? So when I'm looking at the candidates I have to use for generating 2 item sets, I can completely ignore D. Right? And now all the candidate 2 item sets are those that do not have do not have D as part of it. Right? So essentially the 2 item sets that we'll have to consider are AB, AC, AE, BC, and BE, and CE. So these are essentially generated by looking at all possible combinations of the frequent 1 item sets. Right? And now that we have these candidate 2 item sets, right? So we run a second scan through the data, and then we count the frequency of the 2 item sets. Right? Now we can see that AB and AE are actually not frequent among these, and therefore we can prune those away. So we have a list of frequent 2 item sets which comprise AC, BC, BE and CE. Right? Is it clear so far? So we started out with all the 1 item sets. These are the candidate 1 item sets. We counted their frequency. We left out the 1 item set that was not frequent, and then from the frequent 1 item sets we generated a set of candidate 2 item sets which could be frequent. And then we counted the frequency of these 2 item sets, and from there we have pruned away the 2 that were not frequent. So these are the frequent 2 item sets. Now from this we can generate candidate 3 item sets. So if you think about it, so the candidate 3 item sets could be ABC, ABE and BCE. So can ABC be a candidate? It really cannot be a candidate because the subset AB is not frequent. Since the subset AB is not frequent, ABC cannot be a candidate item set. And likewise, can we look at BCE? Can BCE be a candidate frequent item set? Yes, because BC is frequent, BE is frequent, CE is frequent. Right? And what about ABE? Again, that cannot be a candidate item set because AE is not a frequent item set. So essentially, we have only one candidate 3 item set, right? And then we count the frequency of the 3 item set, and then we find that it's actually frequent. So now we have the complete set of all frequent item sets. So the 1 3 item set, which is BCE, 4 2 item sets, and then 4 1 item sets, which are all frequent. So we don't have to look for larger item sets, even though it's potentially possible because we do have 5 elements, 5 unique items, but we don't have to look for any further frequent item sets because there is only one frequent 3 item set. So the a priori property allows us to prune the number of candidate item sets that we will have to generate. So, but still there is a problem in that. So every time we generate a candidate sets of larger size, we essentially do another scan over the data. So the more recent algorithms try to minimize the number of scans you have to perform over the entire data set, because that's a very expensive operation. This is a big challenge, but there are one other caveat which I want to point out. So scaling up to large data sets is a big challenge, but there's one other caveat which I want to point out. So high confidence is not always a good idea. So we have to be really careful about what we mean by high confidence, right? So I can say that somebody buys games, right, implies they buy videos, okay, with confidence of 66%, the support of 37%. So this is something that was actually observed in a real data set from a video rental company, which also were selling video games in the shop. Right? So this is so from the real data, they found that if somebody buys games, then they will also buy videos with a confidence of 66%, okay, and support of 37%. So essentially, it means 37% of the people that came to their shop bought games and videos, and 66% of the people who bought games also bought videos. But then if you just look at what fraction of their customers bought videos, right, that is 75% of the customers actually bought videos. Right? So even though this rule has a high confidence, okay, you can see that if you buy a game, right, it actually implies negatively on buying videos. Right? This is a video store after all, and so people typically come in to buy videos, but the occasional person who comes in to buy a game is not that interested in buying videos. So it actually implied a negative correlation, and if you had just blindly been using support and confidence to determine rules, then you would have actually picked this out as an important rule in terms of having a high confidence. Right? So one measure that people use instead of confidence and support alone is known as lift. Okay? Lift is essentially the ratio of the confidence of the rule to that of the default rule. So if you have a lift of 1, that means that it really does not imply anything. I mean, so whether A happened or not, B is always going to happen with the same frequency. So if A implies B has a lift of 1, then it is not a significant rule. Right? But if A implies B has a lift much larger than 1, that would mean that, so the things tend to, I mean, A is truly an indicator of B. Right? But again, if you think about in this case of games and videos, the lift will be lesser than 1, in which case it indicates a strong negative correlation. So lift is a useful measure to have. And but lift is not the only measure that people have proposed. There are a variety of different measures which people have proposed to analyze association rules, and association rule mining is a very active area of research. Right? So this is essentially just an introductory module, and if you are interested in association rule mining, you should spend more time and looking at the various modifications and additions that people have come up with over the years. So just to summarize, the major challenges in association rule mining is how do you extend this to millions of transactions, because there could be billions and billions of potential item sets. So how do you do the pruning efficiently? How do you minimize the number of passes? How do you reduce the amount of memory that is required while you are doing the counting? So there are many rules, many issues that you have to consider in applying this to large data set. So we have talked about transactional data now. So it's in some sense easy to count because there are discrete events that are happening. But what about continuous data like time series data and images? And how would you go about even identifying what are appropriate items over which you will be doing this counting, and or data with a rich structure like graphs? So frequent pattern mining in graphs is a very important topic which is used in diverse areas like drug discovery and social influence prediction and so on. Right? So how would you can you leverage the structure, or can you make computation more efficient and such structured data? So that is something which is a very active area of research and exploration. Right? And one important twist to this whole frequent pattern mining issue is that we are not sometimes not interested in frequency but in significance. Right? So if A occurs, let us say, in 0.3% of all transactions, right? But when B occurs, it occurs in 1.2% of the transaction. So that means B implies A, right? And that's a significant effect because it improves the frequency of A from 0.3 to 1.2, right? And A might be the needle in the haystack that we are looking for, and finding B actually gives us a greater evidence for the presence of A. Right? So such patterns are significant, but if you just go by the frequency alone, these are very infrequent occurrences in the data. So how do we actually look at such frequent, non-frequent but significant pattern occurrences in the data? So that's the big challenge in the association rule mining community. And again, like I said, it's a very active area of research and people are looking into it. So that brings us to the end of the